Bachelor's degree from Harvard. I wouldn't mention that you worked with Untitled Chapter. Good Canadian. Oh, okay. And then a PhD from Interplay, where she worked with, I should have asked Jerry to say his name, Granovsky, and T.Y. Ram, NSF, and other postdocs at a variety of very prestigious places on the West Coast.
I gave my East Coast dues and then back to the West Coast.
That's true, it was nice. Okay, and now is at UC Davis. I wrote down all your research interests, but I want to say something. Combinatorial representation theory, algebras, quantum groups, categorification, and any other things which we're going to hear.
Great, thanks. It's a great honor to get to be your first colloquium of the school year, and Barbara and Satine have been amazing hosts so far. You got me work out one. So, all right, combinatorics, categorification, and crystals. So I was looking over my slides and I was like, oh, they weren't maybe as grad student friendly as like they should have been. So I kind of scrambled and I said, let's start with something sort of nice. Oops, I didn't get there yet though, sorry. So I'm going to talk about, so categorification is a word, those of you that know it, but to a lot of people, they're like, I don't really know what that is. So I'm going to try to be a good reporter and give you the what, why, when, how of categorification. And then after I hopefully convince you that there's good answers to all of those questions, where I'm really going to focus on is, as you know, the symmetric group, type A, I think my favorite, there's lots of combinatorics, symmetric group, and factorial permutations of 1 through n, best thing out there. I think all the research I've ever done has something to do with the symmetric group or related algebras. Okay, and lots of combinatorics there. And so crystal graphs are a nice combinatorial gadget that comes from Lie theory and quantum groups, again, in Lie theory, and that's really where I'm going to focus my attention. So let's start with the combinatorics. So what have I drawn here in not very good teaching, but it's better than being hand-drawn. So I am drawing Young's lattice of partition. So a partition, so let's just take this fourth column here. What I really mean is I want to write 4 in all the possible ways that I can as the sum of positive numbers. So I can add 1 plus 1 plus 1 plus 1. Well, let me just decide that by saying, okay, I'll make a row of 1. So it's called the Young diagram, Ferris diagram, or I just call it partition. Or I can take 2 plus 1 plus 1, 2 plus 2, 3 plus 1, which is 4. There happen to be 5 of them. And so you can, keep going, write down the partitions of 5, partitions of 6, and so on. And then how am I connecting them? There's 2 ways to think of it. One is if you line up their upper left corners. If one fits inside the other, you draw an edge. So for instance, if you try, there's no edge from 1, 1 to 3, because it would hang out at the end there. It wouldn't fit inside. Or another way, if you're thinking of that sum of numbers, going forward, you just add 1 to one of the numbers. Or you think of a 0 as being add 1. And of course, to make sure that addition is commutative. So I can sort these numbers any way I can. So I do them weakly decreasing. I put all the 2's on top and the 1's and so on. So you might have to resort after you add 1 to something. So that's the rule for the edges. having done that rule, you could probably hand this to like, I don't know, like a 7-year-old, and they could probably just keep going forever. And then they could count all these different things, right? So this is a great fun like graph. And you're like, well, what does it have to do with mathematics? Lots and lots of great stuff. So my favorite place to see it is in the representation theory of the symmetric group. I said I love symmetric group. And so it's not just a graph. So so each of these nodes of my graph stands for an irreducible representation of the symmetric group, characteristic 0. That just means a vector space that, well, in this case, a vector space that S4 is acting on. In this case, it's a vector space S3 is acting on, S2 and so on. It's this kind of graded structure. Okay. And if you think about it, that's okay, because Sn minus, S3 sits inside of S4. Just take the permutations at fix 4. Well, they still move 1, 2, and 3 around. So how S3 sits inside of S4. Okay. Well, the fact that S3 sits inside of S4 means you get two really great functors, induction and restriction. If you haven't taken representation theory, I'm not going to describe induction to you now other than say it's adjoint to restriction. But restriction is easy, right? You just say, oh, I have a map from Sn to endomorphism of vector spaces. Just restrict the domain to Sn minus 1. Boom, it's a map from Sn minus 1. So that's a great functor. And that graph is telling me what's going on with these functors. So again, I said restriction's the easiest one. No, so I take this irreducible representation indexed by 3, 1. It has 4 boxes, the representation of S4. And now I say, let's only take those permutations at fix 4. How does that act? Well, it might not be irreducible anymore. It might break up into some representations. It actually breaks up as a direct sum. So working over characteristic 0, everything's semi-simple. And the representations that you get, you happen to have 2 of them. And we're attaching the diagrams, 3 and 2, 1. And actually, the way the graph is made is by saying, let's say the representations, they're there, they exist. It doesn't matter what you call them. And you restrict them, and they restrict to these irreducible representations that exist. And then whatever names you gave them, this would be the underlying structure. And then you look at the rule, and you're saying, partitions are a great way to name the irreducibles because they capture, the edges are so easy combinatorially to draw here, whereas figuring out that function and what's going on with restriction is maybe more complicated. So this is, this is what I do, combinatorial representation theory. Take something algebraic or representation theoretic that's, deep, interesting, abstract, hard, whatever, and make a puzzle out of it. Okay. And part of what makes the graph fantastic and work is that this restriction has this, I call it this multiplicity-free phenomenon, which is, okay, it has many, many direct summands, but this guy does not occur twice. And whenever that happens, whenever you have multiplicity-free phenomenon, you should be looking for nice combinatorics to come out. Okay, so that's something hopefully you'll learn today. And another way to say it only occurs there once and not twice is to say, well, what's the Hom space of this representation of the restriction? Its dimension is 1. And I mentioned induction and restriction are adjoint to each other, so writing things in terms of Homs is good. Also for when I soup up the situation later, this is the right way to write what's going on. When we get, for instance, non-semi-simple. Okay. Staying with combinatorics, I'm going to take, so what happens is you draw this graph, and by the time you get down here and you're like S17, and you're like drawing all the partitions of 17 and checking you haven't dropped any off and like what's going on, you run out of chalk. And so you're like, is there a more compact way to write what's going on? And one thing you can do is you can label the diagonal of the diagram. And yeah, I have a little bit of chalkboard here. We're always putting the upper left corner here. So this box is 0. So any boxes along here is 0. Any box here, 1, 2, 3, 4, -1, so on and so forth. Because I always make my partitions top heavy because addition is commutative. If I add a number on a diagonal, if I add a box on a diagonal, there's only one possible way to do it, right? If I tell you I add a box on the 0 diagonal, I'm not adding it over here, I'm adding it up here, being flush. So I just label the diagonals and I tell you the diagonal labels, and now I put them on the arrows, then that's the same information. And representation theoretically, it means I'm focusing more on the morphisms then I'm focusing on the objects. And that's also kind of a theme here, is that, you know, you tend to be very object-oriented. I don't know enough about computer science to make that a good joke, but it's really good to focus on the morphisms. And now that we've done that, you can say, oh yeah, you know, I can just label the edges. I can think of these edges as being colored by the integers, because, well, I've decided what integer label. And so in this way, this graph is exactly the same graph as we started with. It looks just a little different, right? We lost the name for this, but we could recover it if we knew where it was in the graph. Okay? So depending on what you're going to do with this graph, maybe you like the other way. But, well, certainly, you know, your 7-year-old's going to like the first one. Okay. But why did I bother to draw it this way? If you read the slide, you already know. Is that when I draw it this way, I'm like, I recognize that graph. I've seen that in a totally different part of mathematics. Totally, but a very different part of mathematics. In Lie theory, there's an infinite dimensional Lie algebra, SL infinity, that has its own representation. And this is a very nice picture of it. Okay, and SL infinity, well, you know, like SL2, 2x2 matrices with, well, for Lie algebra, trace 0 versus determinant 1. So you just kind of make that infinite. I'm not going to make that precise exactly. I mean, but, so it has a representation. And how is this a picture of it? This dot, it used to be a whole representation of S4. So it had some dimension, it had some action, it had that information. Now all I'm just recording is dot. It's a vector. It just smashes down to just one vector that stands for what used to be a whole, not even just a vector space, but an S4 module. Okay, so I replace something that has wonderful, complicated, rich, intricate structure that has morphisms, etc. I replace it with a vector. Okay, and what are the arrows? I made a big deal out of the morphisms. What's going on with the arrows here? Well, what's going on is that, well, SL infinity has its generators, and it's telling you how those generators are acting. So it's just a linear. So basically, I'm just saying there's an operator. I'll use one that you can see better. There's an operator called, you know, F1, and it sends this vector to this vector. And so what, I can't remember what I put on the next slide exactly, but what I want to sort of, what's going on in this talk is the interplay between the first graph and the second graph, okay? And so you might say, oh, wait a minute, I just learned that if I take the representation theory, the symmetric group, something that's, you know, more than 100 years old, Frobenius and Schur knew everything I just said. Because this more modern thing that SL infinity acts on that. SL infinity acts on the representations of the symmetric group. And these operators, EIs and FIs, are kind of like these functors of induction and restriction. You know, that's really cool that that happens, okay? But that's actually, but what if I had come at backwards? Let me see if I said that. You know, what if I had said, oh, sorry, that representation was called the basic representation, B lambda naught, that's what I'm calling it. What if I had started with that, right? What if I had started with, I said, let's take SL infinity, boom, here's a representation. Find me some algebras such that, and find me some functors, such that I can replace this vector with a whole R module. And find me functors so that the way these operators act are kind of saying what's happening with that functor. Because, right, these are linear operators. Functors are richer, okay? That's really hard to do. It's really hard to do. That's what categorification is. It says, you know, let me, so it's easiest to recognize if you already know the answer. But if you don't know the answer, how do you go backwards? How do you invent the symmetric group if all you ever knew was Lie theory and you'd never seen the symmetric group before? How would you come up with an algebra that has branching rules that look like this graph? People have done it, yay. Okay, and that's hopefully by the end of the talk I'll get there, but if I run out of time, that's okay. I'll just tell you right now, any way that you could like generalize this Lie theoretically that would be natural, it's been done, and it's amazing, and it's a wonderful result. Okay. So, oh, right. So, And yes, so can we generalize it? Yes. Oh, and should we generalize it? Is there a payoff? Is there a reason? Is it just fun? Of course, you learn much more about math and the world. And I'm hopefully going to give you some other applications out in related areas. Okay, so I told you I do some what, when, where, how, why, who, and how for that. So what is categorification? Other than just kind of the example I gave you. So basically you replace, say, set theoretic statements with category theoretic analog. So, or it doesn't have to be set. You know, we took a vector, replaced it with an R module or S4 module. So you're replacing something with something with more structure. In general, though, sets tend to become categories, functions become functors, equations become natural isomorphisms of functors. And if you know 2 categories, 3 categories, you can kind of keep going. Morphisms between morphisms. Okay, sorry, there's a lot of text on a lot of these slides, just as this kind of colloquium style, but I'll try to not have you fall asleep reading too much text. But some of the history, the term categorification was introduced by Crane and Frankel, okay? And they were interested in using quantum groups. They were interested in producing 4-dimensional topological quantum field theories. So you might have heard people talk about TQFTs or TFTs, something. These are sort of gadgets that turn topology into algebra. So for instance, you know, there are like nifty kinds of like 3-manifold invariants and 4-manifold invariants. And a lot of people care about them. People in this audience, I'm pretty sure I know a few that care about TQFTs. Okay, and so they wanted to, quantum groups enter somewhere, and they wanted to create a categorical analog, so categorified quantum group. And so one of my goals today is to kind of say, yeah, you can categorify quantum groups, and this is a little bit how it goes. And if I don't get there, again, I told you it can be done. All right, so what is categorification? Well, categorification is like, you know, undoing, it's going from the second graph to the first graph. It's much easier to describe decategorification, the easy way, and then say, oh, just undo that. Like in calculus, your students learn to differentiate before they learn to integrate. And you say, oh, fundamental theorem of calculus, just undo that. So let's say you have a category, how could you decategorify? There's a couple different options. They're well defined, but you have a couple choices. There's this notion of called taking its growth and d group. It has to be a nice enough category for this to make sense. You take its growth and d group, or its split growth and d group, or you can take its trace, which also might be called the zeroth Hochschild homology, or its cocenter, depending on who you are. And I like to use the growth and d group, the G one, because I like working with finite dimensional or finitely generated modules. I like working with simple modules. The split growth and d group is good if you really like working with projectives, projective and decomposables, which a lot of people do. Because I'm combinatorial, I kind of like to work with finite dimensional. And so what you basically do, you have a category, and then you look at isomorphism classes of objects. So you smush them all together. So in some sense, you've gotten rid of a lot of your morphisms. And then you mod out by basically, well, it's like pretending all exact sequences split. You have an exact sequence, assume, you know, say that the isomorphism class of B is the same as the isomorphism class of A plus C. But you know, if that exact sequence does not split, you should not expect that to happen. Okay, so you lose some structure. And decategorification, so this is an algebraic way of decategorifying. You could, in the geometric setting, say that analogs of this might be, you know, take a topological space and take a homology group, right? That's not taking the space, that's just taking a little bit less information from it. And there's a way of calculating by, you know, taking something and modding out some relations. Or you might take equivariant cohomology or Euler characteristic. You know, all these things you do in topology, you can think of them as like a decategorification. And then again, categorifying, if it's undoing it, think about, you know, someone gives you someone gives you a cohomology ring and says, what space is its cohomology? That's tough. Okay, so let's start with an easy example of decategorification. So my category is vector spaces. So I really should say finite dimensional vector spaces over, actually, I don't care what field, called field K. And I claim that when we take its growth and d group, we get Z, the integers. So because isomorphism classes of vector spaces, K to the n is isomorphic to K to the m, only if n is equal to m. Oh, my isomorphism classes are just non-negative integers. But then I put in this relation And so that's like, oh, I'm actually making a Z module, right? So I get negative as well, virtually, right? And so the fact that you can take direct sums of vector spaces, the sum of the dimensions is the dimension of the sum. And so that means you get direct sum becomes plus in Z, and tensor product becomes multiplication. So you get Z not just as a group, but as a ring. And that's great that you can have these extra structures, these extra algebraic structures, both in your starting category and in your decategorified space. And you might have to pick and choose which structures you want to keep, and you might have to throw some others away if you're not as brilliant at categorifying, because we get them all that you want. Another category, graded vector spaces. Okay, it's graded by, let's say you're graded by the integers. Okay, well then I claim you're not just going to get Z, you're going to get Z adjoin Q inverse. You're going to get polynomials. They're all polynomials because, right, the coefficient of Q, you know, the coefficient of Q squared, oh, let's say Q to the fourth. The coefficient of Q to the fourth is just going to be the dimension of the fourth graded piece. As opposed to before, you just have a you'd have a four-dimensional vector space, which is say 4. Okay. And again, decategorification, easy. Or, you know, your category might be R mod for R, some ring, or algebra. And then when you take the Grothendieck group, one way you can think of it as a Z module is just take the Z span of the simples, which is what we did before. When you just have vector spaces, you only have one simple object, a one-dimensional vector space. You take the Z span of that and you get Z. Or if you want, especially if you're in semi-simple land, if you just care about the simples and you just make them additive over exact sequences, characters behave that way. So you can think of it as the Z span of the characters. Okay. So I love the symmetric group. Let's say we take S4 over any field of characteristics 0. I put Q, you could take R, you could take C, it doesn't matter. Just don't put FP in there. Well, you can if P is big enough. And then with the Grothendieck group, well, just a Z span of the simples. And if you paid attention to the first slide, the simple objects were indexed by that fourth column of all the partitions of 4. There happen to be 5 of them. I'm just taking the Z span of them. Okay? So these characters chi mu, or mu is a partition of 4. This is how my notation for those partitions I had in the fourth column. Okay. Now you might say, I don't like Z modules or abelian groups or whatever you get. Maybe I like vector spaces. So you can, well, Z is the universal ring. So you can tensor over C and turn it into a vector space if you want the Grothendieck group. Okay? But when you do that, keep in mind, it came from the Z module. So not every vector space comes from a Z module, but this does. So whatever basis you had over Z and made it rank 5, this guy is dimension 5, but it has a distinguished basis coming from the simples. And that's important. Why is that important? Well, because if you hand me any other module, it's made up of simples. Maybe it doesn't split, but it's composition factors, right? They're the building blocks. So, you know, if you express anything in terms of simples, you're going to have positivity and integrality properties. Any questions so far? Okay. Okay, so now, that's some decategorifications. Let's do a categorification example. So, okay, we know how to categorify the ring Z. Let me take a more interesting ring. I'm going to take the ring of symmetric functions, or algebra of symmetric functions. So symmetric functions, I just need to have a bunch of variables, x1, x2, x3, etc. So like x1 plus x2 is symmetric in 1 and 2. If I have an infinite number of variables, I have to take x1 plus x2 plus x3 plus x4 plus x5. And you do that kind of formally. Or maybe x1 squared plus x2 squared. If I swap the subscripts, I get the same thing back. That's symmetric. Okay, if I get x1 plus x2 squared, not symmetric, unless I add more terms. It's graded by degree, right? I have the things of degree 1, things of degree 2, and so on. And it's graded dimension. I just wrote down there as a generating function. Okay. And I want to categorify that. So I'd like to come up with some category whose Grothendieck group looks like the ring of symmetric functions, which means it should have something like a direct sum, maybe, or a tensor product that will descend to my plus and times here. In fact, It's more than an algebra, it's actually a Hopf algebra, so maybe I want something with a sense to coproduct as well, those, and antipode, if you know Hopf algebra. Symmetric groups happen to categorify symmetric functions, okay? So if I take Sn modules over all n, again, field of character 0, and I decategorify, I get, well, even the n's line up. So for a fixed n, I'll get the degree n piece of this. And then, of course, it's graded. I throw together all the n's, and I get my symmetric function. And how does it work? My irreducible character, which I said I could think of this as the z-span of the characters, goes to a particular symmetric function. If you've ever studied symmetric functions, you've probably run into Schur function. Or maybe for like Weil character formula, it's like a Weil character. If you haven't, don't worry, it's a very special symmetric function. You wouldn't think to write it down as before. If I just told you to write down a couple symmetric functions, it wouldn't occur to you off the top of your head, but they're wonderful. Okay. If you've studied Schubert calculus, I know you've seen them. All right, this map is a Frobenius characteristic map. Also, you can define it really, you can just take any class function here. Right, the Spanish character is a class function. You can take any class function here, and you can write down this map very explicitly where it goes. You don't need to tailor it to this basis. Okay, but this basis is the basis we like. Okay, now again, as an algebra, on this side, I get to multiply together. Right, you multiply two symmetric functions. It's again a symmetric function. What does that correspond to on the left-hand side? I could say, oh, it's this funny product. I'll just call it circle product. But what is it? Well, I've got representations. I got a representation of Fm and Fn. And you know what happens if you multiply something of degree m with something of degree n? You get something of degree m plus n. So I want to take an Sm and an Sn representation, get an m plus n representation. Well, induction is a functor that does that. That's the one that's adjoint to restriction, in case you didn't know it. It's a harder one. Okay, well then what happens with restriction? Oh, that's the coproduct, but you have to sum up overdoing the restriction in all possible ways of splitting m plus n. Okay, so there's an example, which again, once you already know it's true, is very compelling and very easy. But on this slide, when we just had the question mark, people weren't like, "Ooh, I know." Okay. Other examples of categorification that I cannot do in depth, like the last example, Kavanagh homology. I think, even if you don't know what it is, you've heard of it. Pretty high profile. It categorifies the Jones polynomial. The Jones polynomial is a quantum knot invariant. So you give me a knot. I want to know if it's the unknot or not. Well, I have a way of calculating very algorithmically a polynomial. It's actually a Laurent polynomial that goes with it, such that if two knots have different polynomials, they are definitely different knots. Or if I take this knot and I draw it in some different way, but it's still the same knot, I haven't added anything, broken it, you'll get the same invariant. Okay, so that's an example of categorification. And the way in which it's categorification, actually its graded Euler characteristic recovers the Jones polynomial. Okay. Elias Williamson, you might have heard of circle bimodules. Maybe you even went to the summer school they had on it at MSRI last summer. Okay, if you don't know what a Hecke algebra is, don't worry about it. It's like Hecke algebra type A. It's like the symmetric group, but you deform it a little bit. Okay, well, you can categorify that and many, many more generalizations of it. Any Coxeter system, the category of circle bimodules categorifies it. Okay, and that's really celebrated work, started by Sergel, but really began going back, very far back to work of Kaj-John-Lustig. Hecke algebra's Kaj-John-Lustig basis. If you don't know what those words mean, don't worry. Okay, Kavanagh, Lauda, Ruquier invented KLR algebras, KLR, Kavanagh, Lauda, Ruquier, not the same KL of Kaj-John-Lustig. They categorified quantum groups. So that was that motivating sort of question in the beginning, and I said, yes, it's been done. They did it. You can read their papers to see how. Okay, so that was the what? The who. I didn't put the who on the original list because it's too many people to list, and if I tried, I would leave someone out and hurt their feelings. But a lot of the stuff I'm saying, Lauda, who's the L of KLR, has a very nice survey article. And I read this in the past week and kind of helped me collect my thoughts. Okay, the why. Why categorify? So like, why would Kavanagh want Kavanagh homology as a not invariant? Well, it's a strictly stronger not invariant. In other words, there exists, I couldn't draw them for you, two knots that have the same Jones polynomial. They're actually different knots, and their Kavanagh homology is different. Which makes sense. You could have two things that have the same Euler characteristic but are different. So this invariant is finer, it's stronger, it's richer. I think that's a pretty good motivation for wanting to categorify. The more structure you have, the more chance you have to be different. And it's also functorial, which for polynomials, would it make, I don't know what you would say to say that that's functorial, but when you have these categories lying around in homology theories, it makes sense to say it's functorial, which means that cobordisms induce maps between homology. Don't ask me about cobordisms. I'll draw a picture of it later that I stole from Aaron. I didn't even draw it, but I'm not an expert in topology. But part of why that works is because now you have morphism that you didn't have before. Just like when you replace this dot with a whole S4 module, you suddenly get these morphisms that you didn't have before, and they're responsible for a lot of what's going on. So going up a categorical structure, you get morphisms or morphisms between morphisms, and they're responsible for like a lot of the wonderful things that happen. Another reason why you might want to do this is you surpass geometry. So I've given some geometric examples. I'm really an algebraist. So for instance, if we look at the fact that the circle bimodule is categorifying Hecke algebras, well, the things that Kazhdan Lustig did and other people did that use them geometrically, they could do Weil groups, but not arbitrary Coxer systems. And by using this algebraic way of categorifying that they couldn't geometrize, because geometry needed something to be well-behaved, something crystallographic, something more natural occurring. And then the algebra one, like, you could sort of bypass that. So categorification, being more algebraic, it lets you move to different realms, okay? And you could say, why categorify the Hecke algebra? Well, it was a way of proving one of Lustig conjectures about positivity of Kazhdan-Lustig polynomial coefficients for arbitrary Coxeter systems that had been proved for other things before using geometry. Okay? So it's very powerful. Why should it be able to prove something about positivity? Remember that basis that we had for, say, SN representations, the basis of the simples. You express things in the basis of the simples, manifest, it's going to be positive. And so when you can categorify, you have really good arguments that things are positive because you've found the most basic building blocks. Whereas an arbitrary basis of a vector space, give me some other vector expanded, it's going to have positive coefficients. I don't know. Okay. Surpassing geometry. Another place we surpass geometry is categorifying quantum groups. It's really half the quantum group, but I'm going to sweep that under the rug a little because it's on my slide. So when you categorify quantum groups, you can do it associated to non-symmetric Cartan data. So the symmetric data is the one that has geometry living in it. When it's not symmetric, not simply laced, you won't have it. So a lot of times if you look in the literature, like if you like work, say, Vazirani and Vassar or other people who do things very geometrically, it'll often say simply laced. And if you're geometric, you often have to be simply laced. But when you do this algebraic way of doing things, you can say, I don't need to do that. You can do arbitrary symmetrizable type, where some really crazy, like as a Kac-Moody algebra, they're really crazy, but you can still kind of type independently, just do it all at once. Okay, so again, you get to surpass the geometry. Other applications, Chuang and Ruquier, you may or may not know their work, they were able to use categorification to make build what are called derived equivalences. So they sort of, they categorified basically a braid group action on, well, really on, say, the symmetric group picture. There's a way of, in that picture, you kind of flip something over a string and you sort of say, oh, these guys are kind of reflected. There's like some kind of a reflection on that graph. And what happens to these two guys on either end of a reflection? I don't know. But they categorified and they were like, oh, there's something interestingly categorically equivalent about that. And you have to go to derived categories, so you have to go to complexes and such, which If you don't know, don't worry. If you do, you're just like, wow, categorification is a really good thing. Look at all these great applications to them of all these great things that were proved. And they proved through abelian defect conjecture using that technology and looking at, well, endomorphisms of functors. So again, the higher structure you have, you know, you don't just have functions, you have functors, you have morphisms between functors. Going up to that level, you're able to prove things that you couldn't prove before. So I'm just trying to say, why categorify? Great math. Also, once Kavanagh homology was there, at categorifying the Jones polynomial, the functoriality of it, Rasmussen used it to give a purely combinatorial proof of the Milnor conjecture. I just grabbed that off the internet. I don't even know what the Milnor conjecture says, but it's got to be good. Okay. Again, why categorify? Going back to our example about symmetric function, if you multiply together two of those Schur functions and then expand them again in Schur functions, which you can do with the basis, but now this guy will be degree m plus n, so you'll have, you know, size m plus n partitions here. The structure constants are non-negative integers. If you just wrote down, which I didn't, the definition of what those Schur functions are as symmetric functions, and you said, I'm going to multiply them and expand, you would not, like, why would they? You'd have to do lots of examples. I don't know. You have to come up with a proof. It's not obvious. Okay, not at all obvious. But if you said, hey, look, these are just decategorified simples, and we said you have a product, this is tensoring. You tensor them together and induce up, and you expand in simples. Of course, you're going to have positive coefficients when you expand. So positivity, boom. Once you categorify, easy, easy, easy proof. Again, geometrically, people who do Schubert calculus, there's also an easy geometric proof of this in that setting as well. So, right, so categorification in representation theory, right, it's going to improve our understanding, explain positivity, explain integrality. We're going to see canonical bases, don't worry about those. Symmetry, certain symmetries that you see, it can explain that. If you have non-degenerate bilinear forms, you have palms between things. So categorification is going to really enrich our understanding. Okay, so that's the why. Questions? Oh, I have more why. Sorry. My 3-year-old nephew would have just asked anyway, why? And then I could have gone to the next slide. Reciproc contrived invariants. So I talked about not invariants, like the Jones polynomial. So reciproc contrived invariants are another family of quantum not invariants. And they include actually the Jones polynomial or its colored Jones polynomial, the Homfly PT polynomial. These other not invariants that you can all see as special instances of reciproc contrived invariants. And those use the representation theory to the quantum group. And so again, if Kavanagh homology categorified Jones polynomials and it was better, then when you have reciproc contrived invariants, you might want to categorify and get something even better. Okay? I stole this picture from Aaron. So what you do with the reciproc contrived invariant is you cut your knot somewhere and you unfold it. So it's like a tangle. If you want to get the knot, just join up the ends again. And you label each strand by a representation of your quantum group, a finite dimensional one. And then your tangle describes some map from the tensor product of these to the tensor product of those. And that is your invariant. And you have to show it doesn't matter where you sort of cut the knot, that you're going to get the same thing. Showing it's an invariant is not necessarily easy. Okay? And again, right, to get the Jones polynomial, your quantum group, just take it to be SL2. It does have to be quantum. Or if G is SLN, you can get specialization of the Homfly PT polynomial. And so, again, if the Jones polynomial is categorified by Kavanagh homology, and that in the reciproc contrived invariant setting just has to do with SL2, if you categorify SL2 or its representation theory, that should kind of fit on the other end of this picture. Okay, that's sort of this relation with Kavanagh homology. And so you can imagine, if you can categorify quantum groups, you can do quite a rich structure. If this is just the SL2 picture, I'm not even just going to talk about SLN, I'm going to talk about G. I'm going to talk about not even simply lace G, right? Arbitrary symmetrizable type. So quite a powerful thing. Okay, the when. Now, no, just kidding. when is it possible to categorify? That's what I mean by when. Okay, well again, when you see positivity, integrality, when things can be explained well by diagrammatics, up to like isotopy, it turns out, if you've ever seen circle by module stuff, or the SL2 categorification, Cabanavallada-Riquier algebras, they draw it in terms of like these pictures, the diagrammatics. And the diagrammatics, the fact that they work, you know, there's something going on there about the categorifying. When you see good combinatorics, that's sort of part of my message. Whenever you see really, really awesome combinatorics, like this multiplicity one feature that let us draw these nice graphs, I think that means there's some categorification that could be happening that we just haven't figured out yet. Right, it's multiplicity one phenomenon. And the multiplicity one, it might be that like you are able to pick out a leading term. Okay? You think Cauchy-Wark crystal bases and canonical bases and stuff sort of do that, Kajan-Lustig bases. So, okay, the how. Take some art, take some insight. Okay, so now that was part one, the what, when, where, why, how, etc. Now let's go, now that I've hopefully convinced you that it's totally worth categorifying quantum groups, let's talk a little bit about that. Which I did a little bit in the beginning. There's going to be some redundant slides here, but maybe we'll be happy to see them again. So, right, so again, if we started with SL infinity, or its enveloping algebra, and its basic representation, which its basic representation, there's a way of seeing it as a semi-infinite wedge of some other nice representation of it, or box space. Basically means, you know, oh, it's like a vector space that has its basis partitions. Okay. So one thing that's nice about it is all of its weight spaces have dimension 1. It's a Lie algebra, it has a Cartan subalgebra, you can make a weight theory for it. Weight spaces have dimension 1. Dimension 1, multiplicity 1, good for combinatorics, good for categorification. Okay? And again, the SL infinity has these generators, EIs and FIs, where I ranges through Z, and you can draw the action of the generators on an appropriate basis. What appropriate basis? Your weight basis. Then you have to worry about scaling. Let's not worry about scaling. And so the way I'm going to draw a graph is an arrow in this way means I've hit it with an F. So kind of going backwards is like E. So E and F roughly undo each other. The reason they roughly undo each other has to do with the fact that they're dimensional and weight spaces, but they do so in an even more rough way. And then if we make a graph like that, we get this crystal graph. So we already knew that that was going to be the crystal graph of it, right? And then again, you say, aha, if I label the diagonals, and then I say, ah, yeah, it's the representation theory of the symmetric group. Okay. And again, the fact that that happens is like, yeah, I can categorify. And again, those edges are my branching rule. I can do that. Right. And so, but so something more happens. Not just are those graphs the same, but I say that symmetric groups categorify the basic representation, right? I mean, I've got those functors, they go with those operators. Okay. And so if, well, there's, okay, except that, wait, what is going on with those edges? They did have those eyes on it. And, you know, when you restrict, right, you might get these two things you have to differentiate. Other than just combinatorially drawing it, we have to make some algebraic sense of it. And you can. There's these operators called Jusis-Murphy operators that make sense of the eyes, or you can think of it as projecting to a particular block, just saying how does the center act, that differentiates. And there's a way of systematically labeling it with the eyes that gets that same picture. No, whoops, all right. One thing that's nice though, once we have that example in hand, once we understand it and we say we really like it and it's a really great example of categorification, you know, was it just a one-off? And so one thing that's nice, even when the weight space has higher multiplicity, for instance, instead of working over a field of characteristic 0, put in characteristic P. Okay? Then you don't have a branching rule. I mean, you don't get a direct sum of simples. Things don't split. And so you're like, wow, weight spaces maybe become really big, and they do. But this dim Hom picture, it's still multiplicity 1, meaning as it sits as a simple, it's multiplicity 1, which means you can still do combinatorics, you can still get a graph. It's a different looking graph, but you can still get a graph. And you can still, and And so the way that so before, we just had to look at I restriction and I induction and decategorify. Now, because we care about sort of simple subs or simple quotients, you have to put these words socle and co-socle there. Socle just means take the largest semi-simple submodule, and co-socle largest semi-simple quotient. And it turns out you only get one thing in there. That multiplicity one structure is saying, yes, I can repeat everything I did before, and it works for the most part like it did. And then that's really good evidence that you're like, well, wait a minute. I didn't need to have this really, really strong multiplicity one weight spaces. I just needed this kind of multiplicity one. So you're like, okay, this has hope of working much more broadly. Okay. Also, I should say, as an application, we learn a lot about characteristic P symmetric group. Characteristic P, if you know characteristic 0 symmetric group, we know a lot. Beautiful formulas, beautiful combinatorics, almost everything you could want to say. It's amazing. You go to characteristic P and you're like, okay, what's the formula for dimension? Totally not known. Recent work of Williamson said even we had a guess of approximating it using Hecke algebras and confoundlistic theory. That guess was an approximation was so far off. We have no idea. Like we know even less than we thought we did 20 years ago. So, right, so let's generalize this nice, wonderful coincidence of these two graphs, this categorification with symmetric group. Let's generalize it. So that basic representation with V lambda naught, we'll stick any dominant integral weight there. Can you do it? Can we take other G besides S till infinity? And not just enveloping algebra, let's quantize. Can we put UQG in there? That's a lot to generalize. And yes, Kavanagh, Lauda, Ruquier did all three at once. Again, the category, the quantum group, again, it's just half the quantum group. That's what the minus sign is doing there. But as bialgebras, they show that the gross and decoupled they get from our module is the same as half the quantum group. You notice that the K naught, not the G naught one, they work with projectives, projective and equipotentials. I always work with simples, but it's still categorified. And with Lauda, we did the combinatorial version of that, which is for their algebras, make a graph out of the simples. Put isomorphism classes of simples. Put an edge between them if you have a HOM there. And the HOM is always going to have dimension less than or equal to 1 because they built the algebra to do that. Some of the first theorems they proved about this algebra were that it has that property, and that meant you could do this. Okay? And they used the symmetric group and what was happening there as inspiration for how to define an algebra. Right? We said, here's this picture, find an algebra. So you start with something you know and understand, and you say, what extra features does it have to generalize? Okay. So, and then in the interest of time, I'm going to skip talking about cyclotomic quotients. Sorry about that. You can ask me about it later. Okay. Sorry, Webster, Tang, and Kashuar. I'm skipping cyclotomic quotients. Okay. And again, the analog is, right, for the symmetric group, we had to glue them together over all M. These Kavanagh, Lauda, Ruquier algebras are glued together over all, instead of it being positive integers, it's the positive root lattice. Okay. Where does the grading come from? Where does the Q come from in UQ? From grading. They're graded, having a gradation. Remember our vect example went to Z? If it was graded vect, it went to U22Q. All right. So KLR algebras, categorific quantum groups, G arbitrary simple symmetrizable type. We have induction restriction functors. Just like with the symmetric groups, go M and N to M plus N with that little circle operator. Well, now instead you can have mu and nu and nu plus nu, which are going to be in the positive root lattice. Okay? And again, it's graded to get that Q. We have this multiplicity one phenomenon that makes everything work. I really think that this is one of the keys to it that makes it work. I'm really biased in that though. So I didn't really tell you what a KLR algebra was, other than what it does and that it's great and wonderful. Klesja has this really nice description of it. He's like, it really is like the symmetric group. It really is a type A kind of object. If you look at the presentation, it's very much like the symmetric group. But if G is of a different type, it's not type A. It's like saying it lives in characteristic E8. The KLR algebra of type E8 is the symmetric group characteristic E8. Yay, what does that mean? Well, let's say G is affine SLP, if you know what that is. Its Dinkin diagram looks like a circle, which you can think of as the integers covering. And then if you say, let's look at the Carolina of type SLP hat, it's like kind of like taking the symmetric group, actually an affine version, but in characteristic P. Oh, characteristic P makes sense. This Dinkin diagram going around by P, characteristic P, maybe gives you some sense of what's going on. And again, why is it like the symmetric group? You have these local relations sort of in rank 2, and they really look like the braid relations you get in the symmetric group. Okay? In rank 1, it looks like the affine. Now, Hecka, that was really their starting point. So going back, so the when can we categorify? Plug for combinatorics. Before the word categorify was out there, I claimed combinatorialists were categorifying right and left. But they like to use the category of set. Give a combinatorialist an interesting positive number occurring in some interesting situation. They'll say, what does it count? So for instance, like those Littlewood-Richardson coefficients, those C lambda mu nu, you multiply an S lambda S mu, you expand it, positive. Tons of great combinatorics. What do they count? Okay. So, or for instance, if I see positive coefficients in, you know, some power series, some rational function, something you write down, you might not expect to see positive coefficients. What do they count? This is my generating function for sim, by the way. So what are they counting? Partitions of 4. There's 5 of them. Or simple S4 modules. Okay. What do they count? So that was actually categorification. So anybody who's done combinatorics has categorified, even if they didn't know they were doing it. Okay. And again, when can you categorify? When you see positivity, integrality, multiplicity 1 phenomenon, which can occur in many ways. In those morphisms, it was occurring. It's a dim of a Hom. Okay. When you see good bases exhibiting positive or bases, positive might come from a simple, might be a decategorified simple. Okay. And I also think when there's really good combinatorics, that's when you want to categorify. Okay. So with who, what, why, how, when, how, be brilliant. Okay.
Is anybody brilliant? Okay.
So I apologize for this question because I'm digging back in my own memories about a decade or so. But many years ago, I looked at T-core partitions, which, as I understand, had a relationship to symmetric groups in a specific way.
Mm-hmm.
Do you get anything interesting when studying categorification? Do T-core partitions tell you anything interesting there?
Well, so in that picture, okay. So, so if we were in this picture for characteristic T, because you said T-core, or maybe I'd make it P because we're happy with characteristic P. So if we're looking at a P-core, we wouldn't have this whole graph here for FPSN. But where would the P-cores be? They would be, actually, if we go into this picture, they would be what are called the extremal nodes. They would be the orbit under the Weil group of this weight in here. There's weights attached to it. They would also be in terms of, so you might know when you take FPSN as an algebra, it breaks into blocks. And over FP, those blocks can be really complicated. The ones for the cores, though, just look like matrix algebras. There's only one thing in the block. There's one simple, there's one projective, they coincide. So it behaves just like the wonderful, familiar, semi-simple story. Characteristic 0 SN, every simple is also projective, is your indecomposable projective, is its own thing in its own block. The center acts on it, and only it in that way, meaning your character table is square. So in characteristic P, the P-cores are playing that role. They're the simplest possible thing. In the Chuang-Ruquier story, again, they're the nicest orbit to follow for this grade group action. Everything is actually Morita equivalent to each other. You just get matrix algebra. So, yeah?
What's a circle bimodule?
Oh my gosh, what is a circle bimodule?
Is there actually do with buildings?
Not off the top of my head. So do you know what a Bot-Samuelson module is? Okay. I think the answer to that would take a long time. It comes from, maybe it's motivated by equivariant cohomology of a point, and looking at like flag varieties and equivariant cohomology. They're sort of inspired from looking there. I tend to think of them.
From the Coxeter group?
Oh, the B that it would be a bimodule for would be your Borel, by the way. If you have sort of two Borels acting. So if you think of a Hecke algebra as B bi-invariant functions on a group, for B being your Borel, a circle bimodule, the bi is like the B invariant action. But I think to answer that,
Yeah, but you said arbitrary Coxeter.
right. So that's for that system. So you can write it all down in terms of the generators, and you make a ring, and yeah, it's too complicated for me to answer off the cuff like that.
Any other questions? Do any simple answer? One.
This may have been the question for your old definition, but so if I care about, suppose I care about symmetrizable transfer algebras coming from geometry, why should I care about the non-symmetric case, other than the fact that Kajda needs to make these wonderful conjectures?
You mean non-symmetric or non-symmetrizable?
Non-symmetric.
Oh, even non-symmetrizable.
Oh, did I mean non-symmetric? No, I mean like.
Okay, you mean non-symmetric. Symmetrizable but not symmetric. Yeah, if you're a geometer, do you care? Well, you might not care about those cases, but the fact that they could build something that worked in the geometric setting and worked outside of it meant it was a pretty robust construction. And you could learn even about the realm where you know when you have geometrization, this algebraization, categorification, is probably teaching you something and exhibiting some structure you weren't aware of, because it's strong enough to transfer over to these other places where geometry doesn't exist. So I would say that might be a reason. Whoops.
That's for tomorrow.
Okay, well, thank you again.